So thanks everyone who's here in person, lots of people on Zoom. So it's my great pleasure to introduce one of the Sussex AI directors, Professor Julie Reeves, Professor of Artificial Intelligence here at Sussex. I'm going to tell everyone about whether we can trust GPT or not. I'm sure lots of people are interested.
Okay, thanks everybody, and thank you, Ivor, and thank you everybody for coming. Okay, just to say, this talk is very similar to a couple of talks I gave last term, both at the Brighton Data Forum and to the IET. So if you did go to one of those, you're not going to hear anything kind of new today. It's the kind of same talk slightly. There might be a few slight twists on it, but very little. Okay, so first of all, the answer is no. Okay, I don't think we can trust ChatGPT, and if that's all you really came to find out, again, you know, maybe that's, you can go and do something else now, or you can kind of stay and spend the next hour with me thinking about why we can't trust ChatGPT. So overview of the talk, I'm going to be talking about, first of all, a little bit about who I am and whether you can trust me. Then I'm going to talk a little bit about generative large language models, the hype, what we're all kind of experiencing at the moment, and the reality of that. And then I'm going to do a kind of short kind of history of language modeling, thinking about early days of language modeling and more recent work on large language models to try to help us all understand why it is we can't trust large language models to do all the things that they say they can do. And think about some of the strengths and weaknesses and pitfalls in using them, and then talk just very briefly about some current ongoing work at Sussex and the future. Okay, so first of all, who am I? That's me. It's a very old picture of me. I have actually updated my profile picture recently on the web, but that's when I first started at Sussex to do my PhD here back in 2000. I think that profile picture's from. And that's just to sort of say that, you know, I have been kind of working in this field now over 20 years. And sort of, I will start with kind of, I suppose, where natural language processing was at that point, and how we've got to where we are today with large language models. So first of all, natural language processing circa 2000, when I kind of came to Sussex to do my PhD. The late 1990s had seen NLP researchers getting really excited about statistics and statistical methods based on large corpora. That's a term we're going to keep coming back to throughout the whole of this talk is, you know, what is a large corpus anyway. Back at the time, we had something called the British National Corpus. This is a collection of text that was supposed to represent English language, newspaper articles, fiction, all sorts of different things which were constituted English text, and it was 100 million words, and we thought that was absolutely massive, okay, back in 2000. And we were very excited about what we could do with that. When I came to Sussex, I came here thinking that I was going to work on something called the prepositional phrase attachment problem. That was what I think I wrote my proposal about. The problem here, we've got two sentences. I saw the man with the gun and I shot the man with the gun. The difference in the kind of attachments of the with the gun. Does the with the gun attach to the man, or does it attach to the action of shooting? And this was the kind of problem that I came with a view to trying to kind of work on methods to solve this problem. Have got a sentence where with the gun attaches to the man, or is it, in this case, got the pars over here, where we see that the preposition seems to attach to the shooting, because it's more likely that you're going to use a gun to do shooting than to use a gun to do seeing. And this idea that there was kind of some connection between the kind of syntax and the semantics, so what the words actually meant, kind of actually led to me getting rather distracted in my PhD, and I ended up working on something completely different, which was getting big at the time, called distributional semantics, which goes back to the linguists in the 1950s who were talking about the fact that words that occur in the same contexts tend to have similar meanings. And here we might be trying to examine how similar are the meanings of the words saw and shot, and we would do that based on what context can we see each of those words in. And here we can see that they do occur in the same context, so that adds something to their similarity. They're both verbs, they're both things that we can do, they're both things that we can do to the man, and they're both things that I can do. But obviously, as we see other contexts that include the word saw and include the words shot, we would see that there were some different contexts that they might occur in, and obviously they don't mean exactly the same thing. But that was the kind of what I did my PhD in, was looking at the different kind of methods that we could use to work out or infer meaning from the distribution of word co-occurrences. Fast forward all the way to 2023, and natural language processing has come a very long way, it seems. OpenAI, ChatGPT promises that we can get instant answers, learn something new, get creative inspiration. Google's Bard promises similar things about how you can collaborate with it, and it's a conversational tool. And we can look, they will tell us, the hype is such that, if you're a business, you definitely want to be using something like ChatGPT because it's going to make you more efficient, save costs, make better content, loads of things, of ways in which you can make your business better by using conversational AI. And here I've got some things that individuals might want to do with ChatGPT. This goes from a website, makeuseof.com, all the things that you can do with ChatGPT. When you're bored, you can get relationship advice. I'd be worried about that one personally. But supposedly that's something which you might want to do with ChatGPT. But I think we're all aware that people will use these tools, or are trying to use these tools to help them write resumes or letters, create content, write essays. Unfortunately, that's what I find as a teacher. And certainly they are kind of widely used in these applications, or could be. But I suppose the question is, should they be used for those things, both in terms of what the results will be, and also obviously there are kind of wider ethical questions about some of them as well. So as I wanted to kind of prepare for this talk, the first time I gave it, so this was back in October, I thought, well, let's go to ChatGPT and see what happens when we try to use it to research a particular topic. And I picked a topic at random. I decided I'd go and find out about Turner and his paintings. And here on the board, there are some, this is the Wikipedia info box, I think, for Turner, showing some of his paintings and giving some kind of information about the artist Turner. I thought, well, in 2023, 2024, why use Wikipedia? Why use Google? Surely we just ask ChatGPT everything that we want to know. So I had a conversation with ChatGPT and started asking it questions about Turner and his paintings, such as, when did Turner paint the picture Fisherman at Sea? And it came back with a kind of quite informative, so it seems, response about how it's painted in 1796 and how it marked the beginning of his career as an artist, and so on. And I did do a little bit of checking. I was like, oh, I wonder whether that will all add up if I ask, when was Turner born? And it does seem that if he was born in 1775, at 20, he would have been 21 in 1796. I then decided to ask, oh, what about this picture of the lighthouse? And actually, I just made that title up. I thought, well, that sounds like a kind of painting that Turner would have painted. It wasn't on my list of pictures over here, but I thought, oh, I'm sure he must have painted a lighthouse at some point. So I asked ChatGPT, when did he paint the picture of the lighthouse? And it came back with the fact that he painted it in 1817. It's also known as Bell Rock Lighthouse. off the coast of Angus, and how it's one of Turner's notable maritime works and showcases his skill in capturing the effects of light and atmosphere in his art. Oh, that's quite interesting. I just managed to pick a kind of random kind of thing and it seems to exist. And that is kind of the problem of using ChatGPT, or part of the problem is that ChatGPT will always sound very confident about everything. And if you don't actually know the answer for what you're looking for, it's easy to just believe what it says. But I thought, well, I'll check out some of this because I'm not entirely sure that this is true. And actually, as I sort of looked into it using my Googling skills, I found out that Bell Rock Lighthouse was actually painted in 1819, not 1817. So it definitely got that wrong. This painting wasn't on any of Turner's list of paintings on Wikipedia or any other list of notable Turner paintings I could find. So why ChatGPT thought it was notable is another question. And there were also a lot of other paintings that I might have been referring to when I asked about the lighthouse. Turner did indeed paint many lighthouses during his career. And actually one was painted in 1817, which was the Eddystone lighthouse. So maybe there's some reason there why ChatGPT possibly got confused. So I carried on and decided to see what ChatGPT would make of this new information. So I gave it the description about Bell Rock Lighthouse that I'd got from Wikipedia and asked ChatGPT to summarise it for me in 3 sentences, and which it did reasonably well, although it was 4 sentences, not 3 sentences. So I did point that out to ChatGPT, and it apologised in its usual fashion and tried again. And then I decided to ask it again the question about when was the lighthouse painted. And now it told me it was painted in 1819, which was different to what it originally told me. This was the information I had given it. So I kind of pressed it about that, and it said, no, it was 1819, not 1817. And I said, how do you know? And it just kept apologising for the earlier incorrect information that it had given me. But it also told me it seems to be a matter of some uncertainty and I should probably check my sources properly. So okay, yes, art, historical records and museum collections probably are more reliable sources for such information than ChatGPT. My second informal investigation of this, thought, okay, what else might one want to find out about from ChatGPT? I decided I asked it loads of questions actually about Rotherfield, which is the village where I live, and it came back to me telling me that, you know, Rotherfield was particularly interesting because there were lots of buildings from the Tudor period, which wasn't something I'd ever noticed before having lived there. But obviously, you know, that was what ChatGPT thought. So I thought, okay, what buildings in Rotherfield are from the Tudor period? So it came back with a nice list. ChatGPT likes lists. Actually, the first 2, I thought, okay, the old post office, that's the picture there. Yes, that is Tudor. And St Dennis's Church, it's not really Tudor, but it did say it's got some features from the Tudor period, maybe. And then it started telling me about the Six Bells pub. I was like, Six Bells? There's no pub called the Six Bells in Rotherfield. I do know about pubs, even if I don't know about Tudor buildings. So I decided to ask it a few more questions about the Six Bells. But it started getting very kind of, well, I said, well, where in Rotherfield is the Six Bells pub? And it gave me this address. And knowing Rotherfield, I was like, well, there is nothing called the street. There's no the street in Rotherfield. And actually, that postcode, I think, corresponds to a completely different road in Rotherfield. And the nearest Six Bells pub is this one here, which is in Chiddingly, about 12, 15 miles away. And the kind of main pub in Rotherfield, which is quite Tudor, actually, now I come to look at it, is called the King's Arms, and it's always been called the King's Arms as far as I can find out. So in many ways this information it was giving me was very, very wrong, and I did kind of keep pressing about it and said, well, TN6 3LY is actually North Street, and again it started to apologise for its incorrect information it had given me, and started to kind of tell me what I'd already told it in terms of its answers. But it was still wrong. It was still trying to tell me that the Six Bells pub was in Rotherfield at this address, North Street, with that postcode. I tried this again yesterday or the other day before this talk to see whether I'd still get the same answer if I asked again. So I said, where in Waterfield is the Sixworth pub? It's now in Church Street, which is a completely different road to any of the other roads that we talked about before. And that postcode is actually another road in Waterfield called Court Meadow. So definitely kind of conflicting information there in lots of different ways. Why does this happen? Okay, that's kind of, I think we're probably all aware of situations where, ChatGPT has told us things which are wrong. But why is it that ChatGPT gets things so wrong? And the thing that we need to kind of all be very much aware of, and I'm going to try to kind of explain how they work, but the main point here is that they will generate plausible responses based on very large corpora. Okay? Generation does not equal looking things up, and plausible does not equal truth. Okay, so they're trying to tell us things that we will believe based on the corpora that they are trained on. And here I've got some of the kind of corpora that do get kind of used to train these large language models, still got the British National Corpus, but commonly things like Wikipedia and Google Books, etc., are used in these very large corpora that we use today. And so we're going to think about what it means, how these kind of language models learn to generate plausible responses. And to do that, I'm going to just kind of go through some of the kind of developments in language modeling over the years. So we're going to go back to sort of, I suppose, the beginning and say, well, when we're talking about a language model, we're talking about things which are computing either these related probabilities, where we're thinking about the probability of a sentence or a sequence of words, or the probability of one word given the preceding sequence of words. Anything that's trying to compute either of those is something that we refer to as a language model. And when this started back in the 1990s and 2000s, the kind of motivation for doing language modeling was it would help in applications like machine translation, where you want to be able to decide between two competing translations into your target language, and you want the sequence which is going to be the most fluent or the most plausible in that language. And so we had motivation in machine translation, motivation in spelling correction. If you're trying to kind of be sensitive to the context when you're doing spelling correction, knowing that 15 minutes from York is more likely in your language model than 15 minuets from York, it would help you be able to suggest that there was a spelling mistake there. And similarly, in speech recognition, being able to know that I saw a van is much more plausible than eyes or fan, which I can't even say because it's so implausible. But it has a very similar speech signal, will help a speech transcription system get the most likely sequence of words. So that was where the kind of motivation and most of the early work on language modeling was. And back in that day, we would have been thinking about, well, first of all, we're applying the chain rule for probability. So if we want to know the probability of a sequence of words, we would say, well, that's the probability of the first word, multiply it by the probability of the second word, given that we've seen the first word, multiply it by the probability of the third word, given that we've seen the first two words, and so on. And back in sort of 2000, we would have been trying to estimate these probabilities from a very large corpus. So if we wanted to know the probability of seeing the word heal after then he appeared over the, we would imagine at least that we could look up how many times then he appeared over the hill had occurred in our large corpus and divide it by the number of times that then he appeared over the had occurred. However, the problem was something called data sparsity, which plagues us in natural language processing. These frequencies quickly become very small and very unreliable, even in very large corpora. Many things are plausible, which have never occurred before. And there's a kind of Zipf's law, which is something that tells us about the sparsity of language, which basically means that half the vocabulary will have only ever occurred once. If you start to think about how many times certain combinations of words have occurred, we're not going to have seen things very often to be able to make reliable estimates of probabilities using a kind of maximum likelihood approach like this. So, wrong computer, make sure I do the one. So early work would have been looking at n-gram modelling, where we say, okay, well, we can only model a certain number of words at a time. So if we want to get the probability of k words in a sequence, we will look at the current word given the previous so many words. If we're looking at a bigram model, we would look at the previous one word, and in more general, we are assuming that the nth word depends only on the previous n-1 words. But there are many limitations of n-gram modelling, which, you know, the last 20 years we've been kind of working on overcoming. You know, largely it's around the data sparsity, and there would have been a lot of work looking at how you kind of smooth these distributions. And also there was a, you know, what we're going to come to now is the fact that, you know, n-gram modelling assumes that your vocabulary items are distinct, but you actually want to be able to share some probabilities between similar kinds of events. The fact that if you've seen dog, you've seen dogs, they are kind of similar words that you want to be able to kind of share some probability between those. And that's where kind of distributional semantics actually comes in terms of combining these two things, the n-gram modelling and things like distributional semantics. The ideas that we had back in the early 2000s brings us to kind of almost what we need to be able to really understand how modern systems work. Kind of core idea which kind of underpins any kind of neural approach that we're kind of going to look at is that words that occur in the same context tend to have similar meanings. So we're going to try to put words in. Originally, we would think about a very high dimensional space where the number of dimensions was larger than the size of the vocabulary. So we would be thinking about how many times a word such as mushroom occurs with poisonous, or it occurs with green, and then we would try to cluster words or find words which were similar based on these co-occurrences. But that idea is kind of what underpins our kind of modern approaches when we start thinking about neural network language models, because they're the kind of representations of words that we want to be able to kind of capture. So anything that's called a kind of neural network language model is using neural networks to model the language. So we're still estimating probabilities of word sequences, and we're training them on very large corpora. The very first neural language model goes back to, I'm going to Bengio et al. 2003. I think this is the first one I can certainly find a reference to now. It's certainly the one that kind of gets referred to in most of the textbooks on speech and language processing, where they proposed a feed-forward neural network as a language model. And the idea here is that we have our inputs, words at the bottom here, and we're looking at, in this example, 3 words at a time. So the current input is the ground there, and we're trying to predict what the next word in the sequence is going to be. And what happens is that you start by essentially looking up, obviously, what your input word is. You have a one-hot vector, which is then projected into this, what's either called here, it's referred to as the projection layer or the embedding layer. And that is essentially going to be our distributional representation of the word. Because we're taking something which is a one-hot vector, which just says what the word is, and projecting it into a lower dimensional space. And therefore, words which behave in similar ways within this network are going to end up with similar representations in this space. You then put it through a hidden layer, and then you have an output layer, which is generally a kind of softmax layer, giving you a probability distribution over the vocabulary. And then you look at what word actually did occur next. You see what your network's predicted in terms of the probability for that word, and you use that to update the weights within your neural network accordingly. And so that's the kind of the connection with distributional semantics that I wanted to make, is that in this embedding layer, what we're doing is we're getting word embeddings, words which are points in high dimensional space. Typically, the number of dimensions might be around 300, and they are randomly initialized with a neural network. Well, or we can sometimes, there are ways in which we can kind of, or we might have trained them on some other network, but in the very first place, they're going to have been randomly initialized, and then we update them during the training of the neural network, trying to predict the words that occur in the large corpus. Is everybody with me? Yeah? Okay. I realise I'm talking to quite a diverse kind of audience in terms of what people already know and don't know. Okay, so that was our kind of feed-forward neural models. Just to sort of mention some of the other things that sort of happened since then. We got excited about recurrent neural network language models in around 2013 with Mikolov et al., which allowed us to kind of model a kind of unlimited amount of context via the kind of the memory within the recurrent neural network. The idea that at the input, you'd obviously look at the current word, but you'd also remember what the previous hidden layer was, and so your new hidden layer would be dependent on both your current input and the sentence history. And so that allowed us to model more context, and then various different versions of recurrent neural networks. I'm not going to go into them all now. Have become popular to try to potentially remember different parts of the sentence. So LSTMs, etc., have been used as well. One of probably the biggest kind of, I suppose, landmark kind of pieces of work was Word2Vec, the kind of thing that people even not working within NLP kind of tended to hear about and think about, oh, Word2Vec embeddings. And this was, again, proposed by Mikolov in 2013. He'd started with the kind of recurrent neural network language model and then realized he could get exactly the same using a slightly simpler architecture, or there were two architectures that he proposed. One was what's called CBEL, which the idea is that you're trying to predict the current word given the context. Again, we go back to a fixed window of context. So if you had a window of size 2, as in this diagram here, you're looking at the 2 words preceding your target word and the 2 following words, and you're essentially taking the representations of those words, summing them together, and trying to predict what the current word is. Or in the skipgram architecture, it looked at it the other way around, which was saying, okay, we've got a current word, we want to predict what the words are that are likely to occur around it. And this was very popular, certainly for the kind of next 5 years, and still kind of popular as a kind of go-to thing. People go and get their Word2Vec embeddings as representations of words. However, there are many limitations of word embeddings, which we were certainly, a lot of which we were kind of working on here at Sussex back at that time. The problems that embeddings mix up different senses of a word. So if you've got many words have multiple senses, such as star, could be a celestial body, or it could be a celebrity. Well, that would just get all mashed together into one representation of the word. You also have different relationships between similar words. Words that behave in similar ways, are used in similar ways, may be synonyms in the sense that they mean almost identical things, or they may actually be antonyms, that's opposites, or they may be related to each other in other ways, such as a dog is an animal. That doesn't mean the same thing, but they are in some way related, or other types of topical relatedness, such as tennis and racket and things like that, would come up as being similar potentially in these spaces, but that's a different relationship than maybe between racket and bat or something like that. So that was, another problem that we were looking at. And the problems to do with composition. How do you put these representations together to make sentence representations? How do we interpret the dimensions? Who knows what any of these dimensions in these spaces mean? And how do we get representations for rare words? I suppose the next big kind of thing that kind of came along, we probably stole it from computer vision. That's what we do with most things. Within around 2016, we became aware of encoder-decoder networks, and the idea that you could use an RNN to encode an input sequence, and then you could decode that representation into another sequence. And this was particularly popular in things such as machine translation, where you might have your input sequence might be your sequence in English, and then your output sequence is in German, and you encode your input from English into this latent space, and then you take that as the input to your decoder network, which will then hopefully, if it does the job properly, generate a sentence with that meaning in your target language. And of course, it's deep learning, so we would go quite deep with the networks, probably not as deep as image processing, I think, and computer vision. It tends to be deeper networks, but certainly we'd sort of look at 8 or 12 stacked networks of these to be able to try to carry out tasks such as machine translation. That certainly was what they were doing around that time in the Google neural machine translation of around 2016. Okay, but from there, the next, I suppose, the big development, which I think is the one that's kind of led to kind of the modern neural large language models that we talk about today. There were sort of a couple of papers, and I'm going to mention both of them here, although Elmo has kind of fallen out of kind of people's kind of consciousness, and everybody just talks about BERT and attention now. But back in 2018, there were sort of two kind of really big papers which started to kind of talk about this idea of contextualized word embeddings. The fact that you didn't just want to have an embedding of a word, such as star, out of context, and that would be its representation. You wanted to have a representation of star in the context of all of the other words in the sentence. So that if star was being used in a particular way because the word sky had appeared somewhere else in the sentence, you would have a different representation of star than if you had this sentence here, the star appeared, and it's going to be something like the red carpet or something like here. We would want to know, have a representation of star that was compatible with that intended sense. And the way that Elmo looked at this was to essentially use a bi-directional RNN to essentially build up a representation of each word, which was for the forward RNN, it's looking at all the words that occurred before it. In the backward RNN, it would be contextualized by all of the words that had occurred after it. So the representation for star also included aspects of the words that occurred before and the words that occurred afterwards. And then you could use that as your representation in the kind of downstream task. But I said that wasn't probably the kind of, I suppose, the in vogue solution. The other thing that happened around the same time was everybody got really excited about transformers. I'm not going to go into transformers here, but essentially we're thinking about encoder-decoder networks. So we've got input embeddings, we're encoding them, and then we're trying to, again, decode into another sequence, such as what we were talking about when we had the stacked RNNs for. But the difference here is that they're using this thing called attention rather than kind of RNNs or LSTMs or anything like that. And I think largely the kind of popularity of these has been the fact that these are computationally more efficient and effective. But the kind of key idea here is that they're using this thing called attention, which allows the representation of a word at any level in our network to be mixtures of the representations of all of the other words. So the attention learns essentially how important one word in the representation is in the representation of another word. And we have multi-head attention so that we can essentially pay attention to lots of different things at the same time. So here we've got a sentence, the animal didn't cross the street because it was too tired. And what you would like to see happen, and in this example it does, in the kind of taken from this blog here, is the fact that it should be paying attention to the animal because they are both referring to the same thing. So knowing what should come after it, it's important to know that it is an animal. If it had actually been referring to a building or something like that, what might come next would be very, very different. So the idea is that while you're training this to predict what words might occur around a word, it needs to know what to pay attention to, and through all of the examples that it's been trained with, it hopefully will have learned to pay attention maybe to the noun at the beginning of the sentence or whatever is most likely it's going to be referring to. The kind of what we sort of became kind of, I suppose, the first of the large language models was this thing called BERT, which is based on the transformer architecture. These are bidirectional encoder representations from transformers. They were obviously desperate for the acronym BERT in terms of them coming up with that. But that's essentially, which just uses the encoder portion for the transformer architecture. So we're not trying to generate another sequence. We're just trying to take a sequence and encode it. But we want to use both the left and the right context of our target word to build representations of those words. And BERT was pre-trained on general language modeling tasks. I'm going to talk about what they are on the next few slides. That's particularly important in understanding how our large language models work. But they're pre-trained to do mass language modeling tasks, and BERT was also pre-trained to do next sentence prediction. And then you would fine-tune them for some other task, such as if you were doing machine translation or sentiment analysis, you would later fine-tune them more. But the pre-trained versions are all looking at language and modeling tasks. What do I mean by mass language modeling? Well, here I've got a sentence. It's a sentence we saw earlier. The animal didn't cross the something because it was something tired. The idea is when you're doing mass language modeling, you take a sentence or some input, you mask out some of the words, and you ask the model to predict what word should go there. Generally, K% of the words you would mask out. In the kind of original papers, Google said that 15% worked quite well. You didn't want it too small because it'd make it too expensive. You didn't want it too large because you wouldn't get enough context. The idea is that the model needs to capture everything it needs to about these words in order to be able to make predictions about what words could go in those blanks. The other task that BERT was pre-trained for was next sentence prediction. So this captures the idea of kind of coherence within a document. The idea would be that if you give it two sentences, it needed to say, do these two words actually occur together in a large corpus, or are they randomly chosen sentences? So we'd have two pairs that were taken from the corpus. The man went to the store, he bought a gallon of milk, and then you'd randomly select sentences that didn't occur together in the corpus. The man went to the store, penguins are flightless. That isn't a coherent next sentence. And you'd need, you'd want your model to predict that these two sentences are more likely to occur next to each other in the corpus than these two sentences. So what are pre-trained large language models? Well, they are language models that have been pre-trained on very large corpora. Talked at the beginning about the BNC being 100 million words and massive in 2000. BERT was pre-trained on Wikipedia, that's 2.5 billion words, and the book corpus, that's an additional 800 million words. And there I've just got a few calculations as to how long, even BERT base, and that's the kind of smallest version of BERT that they proposed back in 2018. At the time, took 4 days on a 4x4 TPU slice. So that would cost about $5,000 at today's kind of cloud hosting rates for that. And many models are much, much bigger than BERT base. This is probably about as small as it gets. Strengths and limitations of something like BERT, well, they're very strong on the tasks for which they've been trained. That's filling in blanks with plausible suggestions. Okay, it's not answering your questions about the pub in your village or Turner paintings. They're very, very good at filling blanks with plausible suggestions. They're very good at identifying whether two sentences occur together or not. Where have we gone since BERT? Because you're going to say to me, well, BERT's not what everybody's using. Everybody's using things like ChatGPT and Bard. Well, there have been very many variations of BERT, all with a BERT kind of in the name somewhere. And then as we started, we talked about the fact that there is the whole sort of GPT family from GPT-3 through to ChatGPT and systems like Bard. So let's just have a quick think about what's new or better about GPT than, say, something like BERT. GPT-3, I suppose, was the first of the kind of GPT models to really kind of get noticed. I think we did notice GPT-2, but GPT-3 was certainly the one that made people start in the NLP world, start to sort of sit up and take notice. Difference between that and BERT, well, it's what's called an auto-regressive language model rather than a masked language model. But that just means that it predicts the next token rather than a masked token. Okay, so it's almost back to where we were with the Ngram language modeling, where we were trying to predict the next word. It's auto-regressive. This has an advantage in that it can have a kind of, it's easier to deal with variable length input, but it has a disadvantage that it's unidirectional. It's very hard to get both of those things and to have variable length input and bidirectionality within a model. At the time, it was 10 times bigger than any of its competitors with 175 billion parameters, and it had been trained on all of this lot of corpora. So that's probably why it did better than the existing models. If you want to use something like this to generate a response to a question, how would you do that? Well, you take a prompt and you just use a language model to predict what comes next and what fills in the gap. So if I say to something like this, when did Turner paint the picture, the lighthouse, we could actually just use that as our prompt and see, well, what does the model think should occur next? Or we could do a little bit of kind of prompt engineering and turn it around and say Turner painted the picture of the lighthouse in and try to get it to fill in that blank. But essentially, we're just trying to fill in the blanks with the words that have a very high probability according to the model, which has been trained on a very large corpus. What could possibly go wrong with that? Well, first of all, let's remember that they've been trained on fiction as well as fact, and that answers can be very plausible without being truthful. And this does, lead to, what people have, noticed in the literature, that large language models are prone to hallucination. That's making things up. They add in words and even whole sentences sometimes, which just have a very high probability given the context. They're not true. It just seemed very likely. Such as when it was saying it was one of Turner's notable maritime works. Well, it just seemed right to talk about his notable works rather than his works, because most of the time when people are talking about Turner, they want to know about his notable works of art rather than ones that nobody's ever heard of. ChatGPT, how is that different to our GPT-3? There's one more kind of addition to what it's doing, which actually means that it does slightly better maybe than what I've so far led us to believe it would do. what they've done, if you look at the OpenAI's kind of information either on their website or in their paper, is they've kind of used an alignment technique, which they refer to it as, which is essentially reinforcement learning from human feedback to make it more truthful and less toxic. They want it to follow user intentions better than GPT-3 did. What does that actually mean that they did? Well, essentially, they get prompts that customers have submitted. They get human labelers to provide demonstrations of what kind of answers they want ChatGPT to give, and they use that to fine-tune ChatGPT. They can get the human labelers to also rank different model outputs, to build a reward model, so that ChatGPT gets good at kind of outputting the kind of answers that it thinks would please the human labelers. And there's also this additional input, that's the policy, which allows it to kind of maximize this reward. Does this actually work? Well, according to the OpenAI's website, it is better than ChatGPT. No, that's ChatGPT is the one at GPT-3 is the one at the top. Instruct GPT is what we kind of all know as ChatGPT. And what we can see is that it's less toxic slightly than GPT-3 in terms of the kind of language it outputs, but it's still not zero in terms of its toxicity. Its truthfulness, well, it's not overly clear what the numbers actually are, whether they're kind of some kind of accuracy number or not, but it looks like it's kind of almost doubled in terms of its performance, in terms of truthfulness, but I don't think 0.4 is kind of really quite how high we would want that to be on any kind of metric of truthfulness. So there's still a long way to go. And similarly with the hallucinations that are being generated by the system, yes, it's down on the original GPT-3, but there's still obviously a lot of hallucinations happening. So when we're thinking about things like ChatGPT, we've got to remember its weaknesses, which are, it's a pre-trained large language model. So it doesn't know or understand anything. It doesn't look things up or carry out any kind of inferences. Words which mean similar things are easy for it to mix up. This is especially numbers and dates, okay, because they will have very similar representations within the large language model because they tend to get used in similar ways. So things like when I was asking it about the address of the pub, that was going to be something that was always going to kind of really trip over something like ChatGPT, because it just doesn't really know the difference between those different things. It's going to have been trained on a very large corpus, which is certainly biased towards a certain time period, particular geographic locations or certain ways of thinking. And, if we're going to kind of worry about it and get into kind of conspiracy theory, or maybe not, we can always think about the fact that the fine-tuning process could easily be subverted. So it would be very easy to do that if we wanted to. So it's something we do have to kind of think about a lot before we kind of use these kind of models. Just to mention very kind of briefly, as I'm sort of coming to the end of my talk, some of the things that we're looking at here at Sussex in the NLP group are things to do with the characteristics of facts and non-facts, which make them more or less likely to be verified or disputed by a large language model. And looking at how that's affected by whether you provide evidence or not. So if you ask it, is this true based on this document? Or if you just ask it whether it's true or not, how is that affected? What kind of information is more likely to be incorrectly generated? And also whether we can use things like the diversity of the responses, the fact that the large language model might keep giving us different responses. That should hopefully be a clue in helping us to assess the likely veracity. Just one little kind of slide on this in terms of some work with a check COVID publicly available data set, looking at whether a document provides enough information to support or refute COVID-related claims. In an ideal world, we would have everything kind of in on the central diagonal confusion matrix, that things which were should be supported are supported. So that actually is quite often the case. We've got 0.95 there. Things which should be refuted are refuted. The problem tends to be when there isn't really enough information to either support or refute a claim. We tend to find that here, this was work with GPT 3.5, but it's the same with other models as well. They tend to support or refute claims, or say that they should be supported or refuted, even though there isn't really enough information. Okay. Just wanted to say, before I finish, a little bit about the future. So I asked ChatGPT about the future as well. I said, what's the future look like? ChatGPT did give a very kind of standard answer. It couldn't possibly know, especially as his knowledge was last updated in September 2021. So I thought, oh, maybe that was a bit of an unfair thing to ask ChatGPT. So I said, okay, well, how will people use large language models in the future? Don't expect me to read all of that. It came up with lots of ideas, though. I think that's the thing to take away from that. And I have actually kind of organised them on my next slide to make it a little bit easier to see. So these were ChatGPT's ideas about how people will use large language models in the future. So my question for you and for us is, how should people use large language models? All of these were things that ChatGPT suggested. And they're kind of my ideas really at the top, in terms of, well, if we're doing creative writing, you know, as long as we kind of say that, you know, we use a large language model to help us, it's probably okay in those kind of contexts. But then we've definitely got some things in terms of decision support, content generation, mental health and therapy. That always worries me when I see that one. And public policy and governance, where we need to be a lot more careful about how we use large language models if we are going to, because of the kind of inherent problems in terms of the kind of content that they may generate. Okay, that's all I've got to say. I think I'm just about on time. So I will ask if there are any questions. It might be good, but yeah. If anybody does have to run, don't worry, just run. I won't hold it against you.
Could you show your second slide again? Because I was confused about the image that you had accompanying that. You showed an image that had the Scottish national capital.
I did, yes.
So what is that? Is that your fabrication, or is
that wasn't my fabrication? Wait a minute. That was when I was actually trying to find out what the truth was. So ChatGPT had told me that it was Bell Rock Lighthouse was painted in 1817. I decided to try and find out whether that was true or not, and this was what I found, which was from the National Galleries of Scotland, where that painting actually is, and it says that it's painted in 1819. So that was the kind of this first clue that actually.
What does your next slide say? Because I thought on your next slide you said not listed on permanent list of paintings on Wikipedia or any other listed. So that doesn't count as a notable.
Well, it's not. It is. So, well, I suppose it depends what is a notable painting.
Right. Okay.
So Wikipedia doesn't list it, and there are other lists of notable Turner paintings. It's not there. But if you do actually look for Turner, the Bell Rock Lighthouse, you can find that that was something he painted, and it is at the National Gallery in Scotland. So it is a painting. What does notable mean? But yes, but ChatGPT obviously thought it was, well, didn't think it was notable. It doesn't think anything, does it? But it was telling us that it was notable. But that was really just because it likes to use the word notable rather than because there's anything notable about that painting, given maybe what other evidence there is on the internet about notable Turner paintings. I'm not an art critic, so I'm not going to kind of get into that side of it. But yeah, based on the kind of what we might normally find from kind of a more.
What I found is when I find a factual error, it's not that's one pattern that was originally interesting, but what I found more interesting is how it deals with, as you exposed, when you interact with it and confront it with its factual error, how it can't update itself and now believe the new fact piece of information. And so it tries to bend over backwards to make sense of its response, and it ends up making more mistakes. It's 2001 all over again, isn't it? Hal's given incorrect information or asked to do something inconsistent, and so it just ends up doing crazy things in order to make sense of it. That's what I found. So it's less useful the more you interact with it.
So it's definitely true. So these new systems are surprisingly bad at and staying within the limits of what they know, definitely, but remarkably good at interpretation of what I don't know your experience, but my experience is I've never been misunderstood, which is quite incredible. So as a sort of linguist, do you have any sense about whether some of those old traditional linguistic theoretical distinctions are in any sense being realized, being respected within these systems, or not? I mean, like syntax versus semantics, for example.
They're not trained specifically to do that, but I suppose in some things they need to potentially. I suppose the idea is that if the syntax is kind of relevant to what should be paid attention to, they will pay attention to it. But we don't really know what it is that they are doing. Now, there is work kind of probing the different layers of things like these large language models, and generally people find that the kind of the lower layers closer to the input are kind of more sensitive to kind of syntax and are better at kind of doing syntactic kind of probing tasks, and the kind of higher levels are kind of more sensitive to semantics. But it's still it's quite difficult to know what's actually going on. Does that answer your question?
Yes.
Yeah, cool. Justina.
Hi,
A real linguist.
I am a linguist. I'll stay here asking questions rather than answering. Julie, as a Sussex AI director, right? How do you strategize our research in AI when you need to compete with companies like that? Is there a point of even competing? How do you see research in the next 10 years?
That's a big question. I think we have different priorities generally to companies. Companies generally want to make money. I'm not saying we don't want to make money, but and I'm not saying that companies don't have kind of morals and things like that either, but there's generally a different priority in terms of so companies want things which can work and can deliver, and will kind of potentially take the technology that's there and essentially be able to build something that's bigger, that's better. So we can't compete in terms of just building a bigger large language model. But what we can, I think, compete in is in terms of trying to understand what's going on and trying to work out the best way of using these things and what they can be used for, what they should be used for. And those kind of questions, which are more kind of typically academic questions. There's also kind of questions around potentially other solutions which maybe aren't delivering quite the right, high performance at the moment, but actually they may be better solutions in the long run, because actually if we want to actually get factually correct answers, or we don't want to kind of completely burn the planet just by kind of building large language models, and we actually think, well, actually maybe there are smaller models that we could build that would be able to do the same thing if we invest enough in those kind of models as well. So I think there are different directions that we can go in, but yeah, going head to head with kind of OpenAI and Google is not really going to kind of lead to good success, in my opinion. Ivor.
Yeah, a question on the kind of epistemic uncertainty of these kinds of models, like they're kind of the NLP equivalents of massive cognition, know what they don't know. Because I think some of the later versions of GPT use ensembles, which is a well-documented way of being able to capture uncertainty between different data sets. So how is that actually being used? Is it in order to try and capture this uncertainty of whether it knows something or not in the current implementations, and where could it go?
To be fair, I'm not 100% sure how it is being used. I can see that obviously if you have different models and therefore you've got an ensemble and you can see that different models predict different things, then that can obviously be something which you can kind of feed into the overall. And a lot of people are doing work, even if it's using the original one, but you actually kind of have kind of teams of ChatGPT agents that kind of talk to each other or organise each other and get different answers, and then you summarize them and things like that. So there are things that kind of people kind of do in that area with kind of, there's surprising amount of things you can do with just prompt engineering and things like that, which I think is a lot of what goes on. But yeah, with my best answer. Yeah. What?
Yeah, what would you say to people who say, okay, yeah, you're right with those systems as they are, but there have been developments like retrieval augmented generation, which mitigate a lot of this. Do you think that chart at the end, you say good for this, maybe, probably not. Do you think how fluid is that? Do you think that RAG? Do you think that?
I think RAG definitely. So this idea that we want to essentially augment the generation with things that we've retrieved from the internet in kind of a more kind of conventional kind of way, and then base the answers on what we have retrieved. That definitely would seem to be a better way of getting accurate answers, and there's certainly a good results in that area. So I think we need to certainly look at those kind of things. I think there's still potentially a problem, and things like RAG can still go wrong because sometimes you can ask a question based on the text and it still kind of makes something up or hallucinates. It doesn't do it as much as when you kind of give it free rein, but it does still kind of add in other information, or sometimes it will ignore the information that is being given just to make something plausible. So we still need to be careful. And I think kind of my personal kind of take on it is that I suppose as much as possible, if we kind of, I suppose, leave humans in control and let these systems maybe help them, then it's probably okay. But as soon as we kind of start removing the human from the loop in terms of allowing them to like actually make decisions or allowing them to actually be somebody's mental health therapist or something like that, and that's when we start potentially running into kind of problems, because there's obviously all the ethical questions around who's accountable anyway in those kind of situations. So that would be my feeling on that.
What do you feel about airline assistance?
Airline?
Yeah, was it Canadian Airlines?
Oh, the one where it made up a completely random kind of policy, didn't it, to answer somebody's question about getting a refund on something, and it came back with them that they could send in their kind of whatever and claim back for it. And basically there was no such policy, but the chatbot had just made it up. I think Air Canada got what was coming to them really, in terms of the fact that they had deployed this system to answer customers' questions, and their system had told them something completely incorrect. I suppose what you've got to think about in that case is what would happen if it had been an actual person had given them the incorrect answer. I don't know if you'd actually spoken to a person at that company and they'd given them incorrect information, whether Air Canada would have had to honour what they said. But at least then there is somebody that's accountable for it who might actually get sacked or something, or reprimanded for having given out the wrong information. So yes.
As I understand it, that was part of their outrageous legal defense. They tried to say the chatbot was a separate autonomous entity.
Yeah.
And was therefore responsible.
Yeah. Yeah, they tried to kind of like just,
outrageous.
yeah. Yeah.
What are the performance metrics of any of these generative models? Like, let's say, if I were to compare between ChatGPT and Gemini. So how do I compare their performances?
How to compare their performances? I suppose it depends what you want to do with them. So in terms of, you can run them on a kind of benchmark set of kind of questions and answers and see what they come back with and see how many they get correct. There's always kind of, I suppose there's so many different things to take into account. There's whether it's actually correct and whether it's kind of fluent text. And so often I think people and also kind of some of these metrics will confuse those two things. If something sounds very fluent and very plausible, you kind of tend to believe it, whereas something which sounds maybe correct but actually isn't said in such good language, then it makes it harder to believe. So
This is the problem we have with marking.
yeah, definitely the problem we have with marking, especially now. But yeah, so any students here, I don't know, we've got any students, well, we have got a few PhD students. Don't worry
Don't need to worry about that.
So don't worry about that. Okay.
That's a question. Yeah, on Zoom.
But yeah, you're right. Thank you. Let's have a look and see if I can. There's a hand raised, isn't it? Where's the chat? There's some chat here as well. Okay. So just looking at the chat. Okay, so I've said, that was one that I thought was that coding research might be probably okay. Can you talk about how you came to this conclusion? I thought that was a more well-defined problem than some other things, and therefore it is something which is used quite a lot in terms of generating bits of code for a particular problem, and that was something which was more well defined, and therefore there was certainly a space for that. I'm not saying that all coding in the future should be done by ChatGPT, but that I can certainly see that there are ways in which it could be used to help people with coding. And you've said about it, somebody else has asked about it varying across languages, and I think that's definitely would be the case, that it would vary. It largely depends on the kind of amount of training data for those languages in terms of the resources. But yeah, there certainly might be variations according to the kind of the grammar or the script as well.
Julie, does Sussex allow the use of Copilot when students are coding for assignments like writing code? Are they allowed to use Copilot?
I don't think they are, but I'm not 100% sure on that.
I mean, GitHub give Copilot for free to students, so I don't
try and stop them.
Yeah.
I don't know what the policy is.
Yeah.
But it's
If you don't, then I'm sure that
There is. I don't know about Copilot. I know that they've got that new policy that's come out that basically says essentially that the default is no generative AI or anything like that to be used in assignments unless a lecturer explicitly permits it, so that students should see that as being the default option, is that those kind of things can't be used. So I think that would be the policy for that as well. But obviously that doesn't stop students using it in certain cases. But I think that's the policy for code as well as for language. But it may be that a particular lecturer that was teaching coding might say, well, actually, this is a tool that everybody's going to use. You just need to learn to use it really well, and would explicitly permit that within their assignment. I think that's what it is.
And that's the important thing, so people using it in practice.
Yeah.
And you need the whole point of university is to train people how to use and understand things, so they need to at least be able to use it.
Yeah.
To understand it.
Yeah. Yeah. Cool. Okay. Is there anything else on the chat? I said that ChatGPT doesn't make inferences. Wouldn't inferences be needed to generate code? Yeah, I mean, it's a good point. I think, looking at how well it does at generating code, but I think in terms of it using a language model to generate code, it's the same as, I suppose, in terms of trying to answer questions based on language modeling. It's potentially not going to, give you always the best answer, or, they may make mistakes. But I think if you're using it as an aid to writing code, I think that was my intention there. And Becky says she's got a question about your no-go area slide. Did you want to speak, Becky?
I'd like to speak, and I'd like to see the slide again, because I thought it was really interesting. And it was such a good presentation. Like, I can't pretend to have understood all of it, but it was really fascinating.
But yeah. So I mean,
just to understand, like, what were the criteria?
This was more my kind of just initial thoughts about it. So in terms of so I'm happy to talk about any of it, and I'd happily kind of agree that maybe some of them should be in different columns. It was just as I originally looked at them and thought that seems okay. I'm more worried about that. So what was you?
Well, I mean, it's because there's like the world is awash with AI ethics guidelines and new EU regulations and so on. And I just wonder what the criteria were that you apply. I mean, like for me, that looks about right, actually, and they're kind of probably not okay. And then a kind of question about, like, well, what does Sussex do about that? What do we, as a kind of community of Sussex, how do we kind of present this sort of normative? How do we kind of cohere around a set of kind of normative agreements on what are the no-go areas, and do we all have to agree on this as a group of researchers? Just be interested to know what you're thinking about this.
Yeah, I mean, I think it's something which, we need to talk about as a community, definitely. And hopefully that's something which within Sussex AI we can kind of establish a kind of community where we can have those kind of conversations and potentially come to kind of agreements and our own guidelines within the university. In terms of kind of, I suppose, how we do that, I'm not really sure, beyond kind of having those conversations. I think a lot of it, for me, is it's about kind of not necessarily stopping people doing research on doing these things and how you would do those things. It's more about thinking about how you then actually use them. It's that kind of, I suppose it's the age-old analogy with guns, that it's not the guns that kill people, and it's the same with AI. It's about how you use the AI, not kind of the AI itself. And for a lot of these things, there are ways in which you probably can use them. You probably could use them within mental health and therapy, even though I put that here as in my probably not okay, because I think there are things, and I've done some things where I've used AI within those areas, but there are probably more questions that you need to kind of answer around what it is that you're doing and who's accountable if something goes wrong and things like that. I'm not sure beyond that.
I think it says something about also thinking about how it works within the kind of university's own kind of research ethics frameworks. I mean, is this something like we have kind of, we use at IDS, we use the kind of Sussex research ethics frameworks. Is that something we could be thinking about embedding these values into? And I noticed Sarah, my PhD student, has put something in the chat about her own training in ChatGPT.
Well, it should be something we should have on kind of some kind of ethical review thing when we're doing projects. So yes, we have to answer enough questions about whether we're testing on animals and things like that when we do ethical reviews. We could have kind of more questions around kind of use of AI. So that would be something. We've got a conversation with the ethics people coming up, haven't we, about tomorrow, about a master's project. So maybe that's something we should kind of pick up with them at some point. So yes, good point. I realise people are probably going to want to leave, so I'm just going to look at Sarah's question, and then if anybody else has got any more questions, please do email me. But Sarah's saying that she's using ChatGPT, trained in the context of legal services. She's tested it in lab conditions, and it gives answers that are hard to distinguish from a human practitioner. So that sounds great. I suppose it goes to that kind of that it will probably can be very, very good and then indistinguishable. But I suppose the point is, if you're using that, it's like the Air Canada case, and then it does make a mistake, who's responsible for that mistake? So if you're kind of giving legal services, and it's something which is a chat bot, and it does actually give you somebody the wrong information, then that's kind of the problem. I suppose it's not necessarily just how likely it is to give the wrong information. Sounds like it's not likely, but yeah. Did you want to say anything more to that, Sarah?
Yeah, no, sorry, I was nodding away. Yeah, no, absolutely agree with you. And actually, the big debate sort of in the legal sector is how to regulate it.
Yeah,
because it's you know it's massive, legal tech and generative AI and judicial decision making as well, and you know, automated decision making, and those it's sort of getting a lot of traction and becoming more popular. So but how do we regulate that, and how is that done safely? And even judges are using it in their judgments, and in sentencing as well. So you can feed in sort of, you know, the key facts, and it can generate outputs and tests in sentencing. But then it's just really applying sentencing guidelines. So there's loads of different spaces in it, but it is about regulating it. Yeah.
Cool. Okay. Thank you. Thank you, everybody. I'm going to stop sharing and shut down the Zoom call. And thank you all for coming. That's fair enough.
Well done. Very good talk.